Hi everyone, and welcome to Chapter 6, which is focusing on linear regression with multiple regressors. We're going to be looking at a couple different things in this module, and one of the things you want to focus on is an example that will help you base and provide an analysis for your work. One example is trying to predict home prices, and there's many variables that help us try to predict home prices. Multiple regression will give you those variables that help us will outline the variables that the impact will have on predicting home prices. Number of bedrooms, as an example. Do they have a pool? How big is the backyard? Square footage? Those types of examples will help us predict home prices. And that'll be the basis of how we're going to be looking at things. So for this lecture, I'm going to go over sections and the outlines number 2 and 3. So we look at, what are we looking at regression? We're using regression to distinguish between predictions, to estimate the effects of what we're seeing happen. Regression can be used to simply summarize data and to show the value of the coefficients. But that's not going to be really the focus of this chapter. What we're looking at is, how do we, as an example, how do we expect what will happen to test scores if the superintendent reduces class sizes? So we're going to have a regression model that will be set up, and in this regression model, it'll help us set up to know if we change some of the variables, we'll be able to predict test scores more effectively. Now, causality, that's a very complex concept. In this course, we take a practical approach to defining causality. A causal effect is defined to be the effect measured in an ideal randomized controlled experiment. So there's a lot of controlled environments that we look at, and we have to make decisions on those controlled environments. Now, subjects all follow this treatment protocol. Perfect compliance, no errors in reporting, but that's not going to be the case. You're going to see a lot of those challenges will exist. Randomization. Well, subjects from the population of interest are randomly assigned to a treatment or controlled group. Now, controlled. Having a control permits measuring the differential effects of the treatment. Are we able to control the types of variables that we look at? Now, the treatment is assigned as part of this experiment. The subjects really have no choice, and there's no reverse causality in which the subjects choose the treatment that they think will work best. Now, let's go back to that class size. Let's assume in this experiment, students are randomly assigned to classes which would have different class sizes. Because they're randomly assigned, all students' characteristics would be distributed independently of the standardization. So we're looking at this randomization, so the test scores. Now, how do observational data differ from this ideal? The treatment is not randomly assigned. Look at the percent that are English learners in the district. Is it possible to satisfy the two criteria by omitting some type of variables? Now, some people think if I omit certain variables, that will make the regression analysis more effective, which is not always the case. We have the control and treatment groups in different ways. Now, randomization implies that any differences between the treatments and control groups are random. They're not related to the treatment. Now, we can eliminate the differences in the percent that are English speakers between large and small classes. If only the systematic differences between the large and small class groups, then we're back to this random control experiment. Now, is there a way to control the effect of the percent that are English and the control of this measurement of how we look at their evaluation of test scores? Now, if we look at randomization or multiple regression analysis, we're looking at this. Consider the case. Here's what we're trying to predict. Let's say home prices. This is the dependent variable. This is going to be looking at our population intercept, or the y-intercept you might see. This is going to be our first variable and the impact of it, the coefficient. And here's one of the variables. Here's the second variable. Here will be the coefficient. And this could be the omitted factor as well. So how do we predict home prices? It's going to be some basis of an intercept. It's going to be looking at, let's say, square footage, how that impact, is it a positive or negative sign there on the overall price of the home? Bathrooms, is that a positive or negative effect? So that's one of the examples you can look at. Now, consider the difference in the expected values. And we look at the population. Population is looking at all the variables that we have. Now, when we look at the population, we're looking at two different variables that we make this analysis. Now, if we have sample data, that's only going to be looked at in a selection of the data that we have available. Now, interpretation of coefficients in multiple regression. So before, we just have this right here that we just established. Now, after, we're looking at the change and what happened with the change. The difference is going to be the difference between before and after. And the difference will tell us maybe the change in coefficient or how the model changed in predicting information. Now, within the two regressors, the OLS estimator solves. The OLS estimator minimizes the average squared difference between the actual value and the prediction value. So this yields the OLS estimators. And we're going to look at two separate problems now for this basis. Now, you're given the following data on 15 observations. So, as again, here's that y-intercept we talked about. Here's the first variable right there, the coefficient. Here's the third variable. Okay, so we have all of this right here. And there's the OLS, the predictor. Estimate the three multiple regression coefficients. So in this example, we're going to look at what does this tell us, this estimation? What is this telling us to establish? We're telling us the impact, the coefficient is a positive 402. And you got 8 for the one variable. So that's what we're looking at. Then we're going to look at the standard error. So you want to be able to calculate the standard error. You want to obtain the R squared and the R2 values. Now, and they also estimate the 95% confidence intervals for B2 and B3 as well. So those are the two variables that we look at, B2 and B3 in this calculation. Now, after this, you want to test the statistical significance of each estimated regression coefficient using the two-tail hypotheses test. Now, we're going to test at 5%, and we're going to look at an ANOVA table as we do this. So this is going to be one of the first problems that you're going to look at. And you're going to establish how you can make differences between those in our analysis. The next problem we're going to look at is looking at this formula below, trying to solve for R squared. Now, R squared is telling us the relationship between how variables are related. And we want to look at how variables are related in terms of their calculation. Now, when we're trying to look at this R squared, we're trying to define as the explained variation concerning all of the variations. So that's in key. So what we look at is how much of the variable, the variation in the variable can be explained from that one variable. So how likely are those two variables related? And when we're able to relate those two variables, that can tell us a lot about the significance of how the two coefficients could be related to the dependent variable. And that can be very important to calculate. So when we go back here, the closer that we are to 1 means the closer that the variation in one variable can be explained in the variation of another variable. The farther away that we are away from 1 and we get to 0 means the likelihood of them having any type of correlation is very small. So we see that there's a lot of challenges we're facing there. Variables that are highly correlated are going to be 1, no correlation are going to be 0, and highly negative correlated is going to be -1. So the differences that we have in between those can show us the relationships that we have. That can be a very important indicator in the multiple regression analysis in terms of our ability to make decisions. So these are some of the concepts that we're covering in this chapter and two of the problems that were established. If you have any additional questions, let me know, but I look forward to your analysis.